and we'll look forward to some discussion after that. Now, for some reason, it doesn't seem to be showing. There we are. Yes, right. So just to mention that part of the reason for giving this talk is that I knew John Fox for a long time, and he sadly died about 8 months ago. And he was one of the outstanding researchers in the area of knowledge-based systems. And I think it's important that we all remember that knowledge-based systems are a very viable alternative to machine learning for building AI systems of all kinds. So hopefully you can see my slide moving on there.
We can see a slide, but it's not on a presentation mode, is it?
It says screen sharing is paused. Why would it say that? Maybe I should resume share. There we go. How's that?
It's good. Yeah, we can see agenda. Yeah.
Great. Okay. So I will talk about the challenges for healthcare, why we're interested in AI and decision support at all, and then some challenges for knowledge sharing. And then a brief discussion about the many different kinds of AI and the reasons that we build AI systems. And then go into a little bit more detail about machine learning with some examples and pros and cons, and then knowledge-based systems, a little bit more detail on that. I've also slipped in a few slides about the challenges of building computable knowledge libraries. And then we'll conclude with some thoughts about whether machine learning and knowledge-based systems are really competitors or whether they aren't, probably complementary. So starting with the challenges facing health and social care. Maybe it's different in Canada, but I suspect that you have problems with rising demand. For example, demographic transition, people are getting older on average, which means two things. First of all, there are more sick people around, and also there are fewer young people to work in health and social care. There are also consumerist expectations. There's resurgence of infectious diseases for a range of reasons. We've seen this recently with COVID, problems around antimicrobial resistance, which we haven't yet seen the end of. In fact, we're probably just at the beginning of that. Problems with poor diet, climate change, war and famine, and rising inequalities. Concern in the UK about rising inequalities, maybe not in Canada, but there's certainly persistence in low and middle income countries in inequalities. And the real problem is that that's matched by reduction in the supply of healthcare. For example, there's difficulties recruiting and retaining clinical staff. And I expect you've seen Atul Gawande's article in the New Yorker a couple of years ago on burnout. And he blames electronic patient records and reminders as being a cause of that. There's increased welcome emphasis on evidence-based and safer healthcare, but that makes it more difficult to deliver healthcare. And healthcare costs are increasing very fast and well above inflation rate. And that's partly because litigation is rising and the costs of that are rising faster still. So we've got some real mismatches between supply and demand in healthcare, which has led people to say, surely what we need is a better knowledge economy. We need to make sure that the knowledge that we have flows better and faster. But there are some challenges around knowledge, and particularly clinical knowledge. The size of the knowledge base, the rate of change, which when I looked a long time ago, 30 years ago, the doubling time was 19 years. It's even faster now. There's variable quality of knowledge. We know very, very well from evidence-based medicine that individual studies, unfortunately, can't be relied on. You need systematic reviews and meta-analysis and summaries of those. We know that people aren't very good at looking at evidence. They tend to underestimate the size of the evidence base. And as a result, knowledge is very unevenly spread across the health and care system. Some places you find very knowledge intensive and very efficient. Other places are much less efficient and you get fragmented care. And there's a real problem with delays getting knowledge into practice. Andrew Ballas showed it was 18 years, and that was a long time ago. It's probably speeded up a bit since then. We need to, of course, be very clear what knowledge is. What do we mean by knowledge? And Alan Newell, writing in the AI magazine 40 years ago, came up with a very clear and short definition. It's the property of intelligent agents that allows them to reach their goals efficiently. So that would be human agents, animals, and of course, AI. Thinking about knowledge in medicine, it's a kind of information that we use to support clinical decisions, but it's the kind of information that's generic across patients. Patient data is specific to an individual patient, but knowledge is information that applies across many patients. And there are two main kinds of knowledge. There's explicit knowledge and tacit knowledge. And really, most of what we're talking about today is explicit knowledge. Explicit knowledge is knowledge that can be shared by reading, can be readily captured and written down and communicated without ambiguity. Whereas tacit knowledge is much less tangible. It can only be learned by experience, it's intuition. It's often passed on through apprenticeship or learning by doing. And I've done my mistake of my share of learning by doing and making mistakes. I make titanium jewelry now, and it's taken me a long time to learn the skills to make things out of titanium and then to achieve these nice colors that you can get through anodizing. So that's an example of tacit knowledge. I can describe it, but it's much easier for me to show you how I do it. So thinking about different ways that, for example, we would help assess the risk that a patient is, let's say, is having is going to have a heart attack in the next 10 years. The traditional way of doing that would be to start with a large clinical data set, use statistical methods such as regression analysis to identify risk factors and scores or probabilities associated with that, and then use those to support some kind of risk assessment process and hopefully risk reduction process. Of course, with machine learning now, we have alternative methods which still are often statistics based, but they're much more complex. They're designed for capturing high dimensional associations and would generate a risk assessment algorithm. It's often quite obscure. It's not easy to understand how that algorithm actually works. All you know is that you feed the data, patient's data in, it will give you a risk assessment, which is probably the most accurate risk assessment you can get, as long as the patient is similar to the patients that were included in the clinical data set. The third possibility is, yes, do some statistical analysis, but then talk to experts and try and help them to formalize what the risk factors are, what they mean, perhaps using knowledge of physiology or biochemistry or pathology to try and come up with the mechanism through which these risk factors lead to the risk. And then you can use that insight or those insights to build a knowledge-based system, which could then again come up with a score for that person's risk, but it's a knowledge-based system rather than a statistical or a machine learning system. Well, let's put the statistical systems on one side for the moment and really focus on machine learning and knowledge-based systems for the rest of this talk. What we need to do, though, is to make use of the knowledge either captured through machine learning or through an expert input. And what we do is we build decision support systems, which, as you know, typically a health professional uses an electronic patient record, talks to a patient, puts the data into the record, and then that record communicates with the DSS, coded patient data, and then there's knowledge in the decision support system, which allows the decision support system to generate advice, a risk score, a reminder, whatever it is, which then appears in the EPR interface and is communicated to the patient and health professional. So that's the standard way of building decision support systems. And there's very good evidence that DSS work. For example, there's a suite of 6 systematic reviews from McMaster in Hamilton, Ontario, analyzing 166 randomized trials of decision support systems, supporting a variety of different clinical decisions. And overall, you can see that the clinical decisions or the care process improved in more than half of the trials, patient outcomes or surrogate outcomes in about a third of the trials, if you're being optimistic, 15 to 30% of those that actually studied the impact on patient health. And the picture there is of the medical school office building in Stanford, where I spent a delightful year back in the 1990s working on knowledge-based systems. And it was the site of a large chunk of research on knowledge-based systems, including the Mycin research program, which we're going to be talking about in a minute. So that's knowledge-based systems and decision support. But what about AI in more general terms? So a short definition of AI, it's an attempt to emulate or substitute for human reasoning. And there are a whole range of different applications, probably more than a dozen broad areas. But one of the most important is natural language processing and machine translation. And often machine learning is a major technique, as well as knowledge graphs and text assembly there. Robotics is another one. Again, machine learning in computer vision, task scheduling, cooperative computing, and other techniques are used there. Decision support systems, again, can be driven by machine learning or knowledge-based systems, and a range of other techniques, which we'll talk about in a minute. Risk calculation is another area of AI. For example, predictive analytics, say, trying to identify subpopulations in a large population who are at risk of alcohol liver disease. And again, statistics and machine learning approaches often used, sometimes also qualitative reasoning, and we'll talk about argumentation in a minute. So a whole range of different techniques that are used in different applications in AI. And again, I think we can already see that AI is not synonymous with machine learning. There's a whole range of techniques here. But let's drill down into machine learning a little bit more. It's about discovering insights or mining associations from typically very large data sets. The original techniques included something called classification and regression trees, or CART, and the ID3 or ID 4.5 algorithm, which Ross Quinlan developed in the 1980s. And then there was a whole lot of interest. At MIT published a book called Parallel Distributed Processing, which was really about what we would understand now as neural nets, and of course deep learning systems now. There are two broad categories of machine learning, as you know. Supervised, which is the most frequent kind, which the dataset includes the gold standard. So you can have preconceptions about what you're trying to predict or classify. But there's also unsupervised learning. There are techniques such as Cohonan feature nets, which are used to almost explore data sets to identify new classes, let's say, of melanoma or some other disease subtype. There are a whole range of pros, as you can see, for machine learning. They're often better than statistical methods for high dimensional data. And you can get outstanding performance from machine learning methods. And for example, beating established master at Go, which is an extremely computationally difficult challenge, identifying melanoma at better performance than experts and so on. Another great thing about machine learning is the potential to continue learning as new data arrives. So you can refine your model with new data. And it obviously reduces the need for expert input. There are some cons. We'll talk about some of these in more detail in a moment. Machine learning methods can be misled, and I'll give an example of that. They're usually unable to explain their reasoning. They may be able to produce a list of the most relevant features that were used in the classification. It's something which Anna Hart and myself wrote about a long time ago now. We wrote about black boxes and the challenges of using those in medical decision making. There is a potential for bias, and Cathy O'Neill wrote a nice book called Weapons of Math Destruction in 2017, really giving a catalogue of areas where hidden bias in the data set led to biased algorithms. And there is this problem that you do require a huge data set to come up with a reliable algorithm and the gold standard for each case. And so actually, although you may not require expert input, you certainly require human input to decide what the gold standard is. A range of examples, and machine learning is very frequently used in speech and text understanding and computer vision as well. And without machine learning, these applications would really be impossible. Games and leisure, we've mentioned the DeepMind's Go champion, the recommender engines in Netflix and Spotify and so on. Credit card fraud detection, algorithmic trading, etc., rely very heavily on machine learning. And these are all example domains where there's huge amounts of data, and that obviously helps a lot. An ex-colleague of mine, Peter Hammond, has been using machine learning in the UK to detect unauthorized sewage discharges. And there's been a lot of work on air pollution forecasts and other environmental applications. And there's been quite a lot of work around clinical decision support using machine learning, typically on image analysis. I won't go through all those, but other applications as well. For example, speech to text radiology reporting system and predictive analytics. Let's look at a case study. You probably know the Stanford melanoma system, which was published in Nature journal in 2017, so a very highly prestigious journal. It was a convolutional neural network trained on 130,000 images, a massive database. And then they tested it on a much smaller imaged test set, which they'd also got 22 board certified dermatologists to look at. And the neural network had a higher performance than any of the dermatologists, with an area under the curve of 0.94, which is really pretty impressive. All those images were checked by biopsy as well, so we know the gold standard for sure on whether that patient had a malignant lesion or not. However, it turned out that some of the test set images included the ruler that dermatologists use to measure the size of a lesion, and that you can see an image of the ruler over on the right there. And this was found later, and there's 2 or 3 articles about this. And the problem is that the chances of an image with the ruler being malignant was far higher than for the other images that hadn't been taken by dermatologists. And this demonstrates the risk of including in your training or test data sets images, in this case from later in the care pathway, and the algorithm would be useful. The idea of the algorithm was that it be made available as an app on a smartphone. People could use at home and point the app at their pigmented skin lesion, and it would tell them reliably whether this was likely to be a melanoma or not. But given that they trained it and tested it using images that came from much later on in the care pathway, that's not going to give you reliable information. So some people have said that the people at Stanford cheated by including these images. I don't think they did that at all. I think it was just that the public data sets of skin images, some of them came from dermatologists, and so they included the ruler, and they unfortunately weren't aware of the importance of this. So that just demonstrates when you're doing machine learning, you really need to know what you're doing and choose your training and test data very, very carefully. So let's move on to knowledge-based systems. So here the aim is quite different. It's to harvest, represent, and apply human knowledge to support problem solving. And there's a very long history going back to the 1960s, when initially people were interested in emulating and simulating human reasoning using what they call production systems, which are basically if-then rules. By the 1970s, a lot of computer scientists got interested in using them to solve problems, and there were commercial systems even in the 1970s. For example, DEC had a very widely used so-called expert system based on if-then rules to help diagnose problems with PDP series and other VAX computer systems. The medical example is Mycin, which Ted Shortlift developed in the early to mid 1970s at Stanford. So that used if-then heuristic rules and so-called certainty factors. But there were other methods for representing knowledge, including fuzzy logic, frames of objects, and Janice Aikens built one of the first medical systems it's called PUF, and it was to do with interpreting lung function tests. The shortcomings of that approach soon became clear, and in the 1980s, deep knowledge, so-called, was added to do with causal knowledge and anatomical knowledge, probabilities, and qualitative reasoning and simulation, and there's various names there. We'll talk about some of those in a minute. And then in the 1990s, a whole range of logic-based approaches were developed. For example, temporal calculus from Allen, spatial reasoning from Cohn and Leeds, argumentation from John Fox, and then deontic logic with the logic of obligation. And I did a small project with Peter Hammond on that in the 1990s. There are a range of different control mechanisms in knowledge-based systems. They started off all being backward chaining or goal-driven, but then data-driven forward chaining systems became popular, and an increasingly mixed initiative and advisory critiquing system views. Again, there are pros and cons of these systems. You can build tools to capture expert knowledge. People have always been worried about the knowledge acquisition bottleneck. Getting experts to tell you their knowledge, to formalize it and express it in terms that the computer can understand is a challenge. One of the great advantages of knowledge-based systems is the knowledge base should be readable. We'll see examples of that in a moment. And that you can build tools not only to capture the knowledge, but also to check the completeness and consistency of the knowledge base. And potentially, if you've got the knowledge in the right format, whether it's rules or facts or some other format, you can then reuse it for other purposes, for example, generating explanations or for teaching. There are some issues about capturing knowledge, though, so-called paradox of expertise, that often experts don't really find it very easy to express their knowledge. And sometimes they prefer to keep it secret. There's a kind of mystique of expertise. Rule sets can become very, very large and difficult to maintain. And Bill Clancy was one of the first people who proposed methods to overcome that. There are other issues, for example, the closed world assumption that the only knowledge that's necessary to know to solve this problem is within the knowledge base and anything else doesn't matter, which is clearly a fallacy. And some knowledge-based systems can be very brittle outside the domain of expertise, unless you include deep knowledge, which would help them to make to reason from first principles. There are a number of solutions. Sometimes you start with rule induction to help the expert try and formalize their expertise. And we'll see in a minute about the problem of readable knowledge bases and distinguishing declarative from procedural knowledge. Model-based knowledge acquisition tools can be a way of overcoming the knowledge acquisition bottleneck, and semantic networks and qualitative reasoning and so on. Again, we'll talk about that. So, some examples of knowledge-based systems. I've mentioned Mycin already. It was designed to diagnose septicemia and meningitis. It was never actually used in anger. It was really a large demonstrator, if you like, to try and explore how to represent a large domain of complex knowledge. And it was very hard to maintain, and it was discontinued after a few years. We'll talk in a little bit in a moment about the Oxford System of Medicine, which is John Fox's project, using a very different approach, very few generic rules, but thousands of facts. And the idea was it would be a tool to help GPs in primary care to think about conditions that they hadn't thought of already when somebody presents with an unusual picture of symptoms. I built 2 or 3 systems in the 1980s and 90s. One was to interpret lung function tests again, and it was to replace a system that was built in Fortran. It was impossible to maintain, and so I built a simple rule-based system with forward chaining knowledge base called ILTARS. I then built a system which was actually a hybrid system using a Bayesian front end to calculate a person's risk of having a heart attack, and then some rules which used that risk and other information about the patient to generate advice on what to do with that patient. This was used in the emergency room in Westminster Hospital for some years in the late 1980s, and we did a trial of that. Another example is Munin, a large Bayesian network to help interpret complex EMG results. And I've got a slide on that. So here's Mycin. There's a picture of Ted Shortliff at a DEC 20 terminal, probably green screen terminal, in the mid-1970s. Ted Shortliff was an infectious diseases doctor at Stanford, and he did this work for his PhD and has stayed in the area of health informatics ever since, health and biomedical. So here's an example of a rule from mice, and you can see it's written in Lisp and it's hardly really readable, but they did write a translator, and the translation of that rule is there. If the gram stain of the organism is gram negative, the morphology is rod, and it's an anaerobic organism, then there's suggestive evidence, 0.6, that the organism is bacteroides. And this figure 0.6 is a certainty factor, and they developed the certainty factor method for representing the strength of the association in this rule. And of course, there are many, many other rules. Here's another rule which also concludes that the infection is bacteroides, but using other more clinical features. So the first rule is about the morphology and characteristics of the organism that's identified in the lab. The second one is about the clinical features and where the specimen came from. The problem with mycin and other very large knowledge-based systems built using just rules is that these rules aren't really modular. And the hope or the belief was initially that these rules would be modular. You just add more rules without affecting any of the other rules. But the reality is that because they're non-deterministic, because they've got this certainty factor, that they're not independent of one another. And if you look at the second bullet point, the real problem is that this formulation, if A then B, all it means is that A is associated with B, which is a very loose kind of relationship. There are many different kinds of association. Does A cause B? Is B a kind of A? Does A define B? Does B follow A? Does it inherit properties of A? Or is it just a simple correlation? And actually, that's closer to the truth. It's really just a correlation. And this means that there are problems. And Julia Pearl at Berkeley University came up with this very nice scenario and a way of depicting a scenario. This is actually from Heckerman and Horwitz's paper on the myth of modularity, which was published in the 1980s, I think. And you can read the scenario. So essentially, somebody hears that their burglar alarm has sounding, and they recall the last time it was an earthquake that triggered the alarm. This is a Californian scenario, remember. It would be quite unlikely here in Wiltshire in England. Driving home, the radio reports an earthquake 200 miles away. So that indeed makes an earthquake being the most likely interpretation of this alarm. So here's an inference network. The problem with this is that Mr. H did hear the radio news, so the alarm sounding supports the earthquake hypothesis. But if Mr. H had not heard the news on the radio, then the alarm sounding lends more support to the burglary hypothesis. And you can imagine, if alarm then burglary, if alarm then earthquake, could each have a certainty factor associated with it in shortlist representation. But the trouble is the certainty factor for the association would have to vary depending on whether Mr. H heard the radio or not. And that's clearly nonsense. So you can see that using a simple measure of association here is really not going to allow these rules to fire correctly, and just adding more rules with different certainty factors, you can see you're going to end up in a real tangle. So John Fox and other people at the time realized that we needed to do a lot more to try and separate out different kinds of relationship. One of John's major contributions, I believe, was this idea of having facts and generic rules. So here are some facts. They all happen to be about diabetes. Some are about symptoms of diabetes. There's 4 possible symptoms here. One is about a test for diabetes, and here are some treatments or possible treatments for diabetes. And those facts wouldn't be very useful at all, but what you need is some rules, and this is more prologue style syntax, but with for all instantiation, which you don't get with prologue. So John Fox and his colleagues built an expert system toolkit called Props2, which allowed you to write really English language like rules and facts. But the important thing is that anything which is capitalized is a variable. So the first rule here says if patient has symptom and the symptom is a symptom of disease, then that symptom is an argument for the patient having the disease. And that will bind to some of these facts and to data, which goes into the working memory. So, for example, here's some data. Mrs. Smith has polyuria. Well, that's one of the symptoms of diabetes, and blurred vision and tingling feet. She also has a headache. Well, that doesn't bind to any, through this rule, doesn't match any of these facts. There might be facts about headache as well. And in fact, in the case of OSM, there were thousands of facts about different diseases, about the symptoms, tests, and treatments for many different diseases. So if we allow the inference engine to run, you can see that it will infer, using rule 1, that polyuria is an argument for Mrs. Smith having diabetes. You can see through, so it binds with polyuria here. It also binds with blurred vision, because it's for all instantiation, and tingling feet. And then, because there are 3 arguments, rule 2 will also fire the number of symptoms that is an argument for a patient having disease greater than 2. Then it will conclude that patient probably has disease. So it concludes Mrs. Smith, the patient, probably has diabetes. But it will also, if you add a test result, Mrs. Smith has raised fasting blood glucose, and we know that that's a test for diabetes. Well, since Mrs. Smith probably has diabetes, will match here, and patient has test result, and test result is a test for disease. So here's the test result, and here's it's a test for the same disease. Then diagnosis, it will conclude that diagnosis of patient includes disease justified by test results. So it will also conclude diagnoses must include diabetes justified by raised fasting glucose. I should probably put some underscores in here, might make it a bit clearer. So that's rule 3 firing. But since rule 3 has now fired, rule 4 can also fire if diagnosis for patient include disease, and it does. And treatment is a treatment for disease, and there are facts here about treatment, then suggested treatments for patient include treatment. So it also goes on to conclude that there are 3 suggested treatments. And the really clever thing of this is that if you ask why, then it can go back through the rules and say, I suggested this treatment includes diet because diet is a treatment for diabetes, and the patient has diabetes. And you told me that, and I concluded that because they had a raised fasting glucose and at least 3 of these symptoms. So you can generate really very plausible and English-like explanations from this kind of approach. The other thing is, because these rules are very generic, they're much easier to maintain. That these facts are also much more modular and individual than in the certainty fact. Now, of course, what you don't have here is any treatment of uncertainty. All you do is you have a number of arguments that you're accepting as being evidence for probably the patient probably has disease. Instead, you can also have negative arguments, and OSM had negative arguments, and you could actually look at the net number of arguments in favor and arguments against, but I've simplified here for the purpose of explanation. If you want to treat uncertainty much more rigorously, then you can use the causal probabilistic network approach. And essentially what you do here is you model the domain. This is an example for interpreting EMG. Sorry, it's not a very good picture, but this is chronic distal axonal neuropathy as opposed to limb girdle dystrophy and so on. So these are various diseases, and these are various findings. So these are the findings that you get on EMG, and then these are intermediate findings, which are kind of physiological entities. Now, each of these nodes actually has it incorporates Bayes' theorem, so it uses both prior and conditional probabilities. And when you start with, before you put any data in, you start with the prior probabilities of these diseases, all of which are pretty rare. And then you can propagate the uncertainty across the entire network using something called the Loritzen and Spiegelhalter algorithm, which is quite complex. It's a message passing algorithm, and it requires you to form a tree of cliques. So this is to do with network theory. But there are tools, obviously, that allow you to do all that. And the good news is that you can propagate this in pretty well real time. As the data comes in here from the patient's EMG findings, then these graphs all adjust, and you end up with the probabilities of the different diseases being displayed. in a very rigorous and principled way. So you don't need certainty factors. You can actually do this rigorously now using causal probabilistic networks. So another good thing that you can do with knowledge-based systems is you can represent guidelines and policies, and there's a lot of interest in evidence-based practice guidelines and how we can help clinicians and patients follow those. So this, for example, is a fragment of knowledge again about diabetes, gestational diabetes in this case, and there are now languages, for example, CQL, clinical query language, which is a computer executable language. Again, it's not very readable, but this is part of this knowledge expressed in CQL, which is computer executable. So you can build decision support systems which give alerts and reminders, generate risk factors and so on, using tools like CQL. In fact, there are lots of different languages for capturing computable knowledge, and particularly guidelines. CQL, CGL, GEM, Glyph, Protege, and Proforma, which was a development of the tools that John Fox initiated. And there's a wide range of tools to help you capture guidelines in the Proforma language. It's not always easy to do that. It's quite difficult for guideline development groups to use these tools, although I was part of an experiment in which we did that in the Netherlands a few years ago. And it's quite a lot of work to capture and formalize a guideline, but actually you don't need to formalize the entire guideline. You only really need to capture the reminders and the alerts. And one of the big issues is that at the moment, decision support system developers construct their own knowledge bases, which is a huge amount of the kind of cottage industry of building a knowledge base before you can build an app or a decision support system. That's terrible duplication. There's also lack of agreement on the standards, too many standards, as we said. And there are some quality and safety issues, and Mark Musen was one of the first to point out that there's often missing information in protocols or guidelines. And there can be variation of results from the same computer guidelines captured independently by different knowledge engineers. This is the trial that we did, in which actually Rick Good, who was a PhD student, worked alongside the guideline developers to capture the guideline in a computable model. And then we did a cluster randomized trial of the impact of that in 21 centers and demonstrated that there was a benefit, increased concordance with guideline recommendations. So one of the ideals that we have and a vision that we have is a global MCBK coalition, Mobilising Computable Biomedical Knowledge, in which we will capture knowledge in an indexed library of knowledge objects designed for a whole range of different purposes, decision support and so on. And it will be captured as knowledge objects, which has the actual payload, the algorithm, the rule, the score, whatever it is, plus a whole range, some metadata, if you like. And those knowledge objects can be used with the search engine by a range of different knowledge users, medical devices, alerts and reminder systems, triage systems, chatbots, medical robots. All these systems need codified knowledge. And at the moment, if you're building a medical robot, you have to codify the knowledge yourself, similarly for medical devices, for drug dose, etc. And the vision is that knowledge authors, a whole range of knowledge authors, from guideline authors to the Cochrane collaboration, patient groups, maybe data mining for learning health systems, medical publishers, will put their codified knowledge into this indexed library. There are some challenges, of course, challenges around sustainability, helping knowledge authors justify that work, as well as building trust of the developers and users by validating the knowledge objects, by preserving their provenance and integrity, ensuring safe reuse. And we know examples like the QRISC-2 example where knowledge object was not safely reused. It was plumbed in badly by a primary care system developer. Keeping the knowledge objects up to date, respecting the evidence hierarchy, making sure that national guideline and Cochrane review objects overrule objects based on clinical opinions, for example, and discussing establishing governance for all this. But we've been doing quite a lot of work in the UK, and there's work in the US as well. I'm not aware of any work in Canada yet, but I'd be interested to hear of any. And there's videos, and also there's a special issue of BMJ Health and Care Informatics with some articles, including one by NICE on this approach. So really drawing things together, which approach should we be using? Should we be using machine learning, as is very popular nowadays, or should we be using knowledge-based systems? Well, this table tries to distinguish them. Ease of development, yes, but you need a massive database. For knowledge-based systems, you need a knowledge expert and a knowledge engineer. You can retrain and update machine learning systems with new data. You can update knowledge-based systems as well, once they're well structured. But if it's something like a Meisen type certainty factor and rules, that can be very difficult. Explanations don't really work very well in the high-risk use case for machine learning, but in knowledge-based systems, they can be very helpful and convincing. We know that small anomalies in input data, for example, pixel loss in images, can really put machine learning-based systems off. Potentially, knowledge-based systems can be safer, and they can even warn you when they're out of the domain, and you can actually reason about safety within a knowledge-based system. Machine learning systems, though, are very, very accurate if they're well built. Knowledge-based systems are usually lower. Sorry, that's my wife going off to a meeting. What are the risks? Well, unintended bias due to faulty data and fragility at the domain margins can be a problem with machine learning. With knowledge-based systems, because the explanations can be very plausible, there's a risk of something called automation bias. And Kate Goddard was one of Abdul's PhD students, very bright student, who published a nice systematic review on automation bias. Basically, the problem is that people might believe the advice from a knowledge-based system, particularly because if it gives an explanation, even when it's wrong, and they would have made the right decision. It's called automation bias. So the ideal application for machine learning is probably a narrow domain, such as image or voice processing with plentiful complex data. For a knowledge-based system, it's where the knowledge has already been codified, for example, clinical practice guidelines, and then translating those into computable knowledge. So that's a very simple aid memoir to choosing between machine learning and knowledge-based systems. In conclusion, AI is definitely not synonymous with machine learning. There's many other techniques used in AI. And the main ones are obviously machine learning or knowledge-based systems. They can be used for developing, either of them can be used for developing clinical decision support and other AI systems, either separately or together. And there's a lot of interest in hybrid systems. There's a great deal of experience in building knowledge-based systems, and many books about in describing the experience with, for example, the Meisen experiments at Stanford. And really the advice, as always, is to choose the technology that you use to match the user need and avoid building a kind of technology-led solution. So, for example, if explainability or modeling policy or guidelines are crucial, then knowledge-based systems may be the preferred technique. Whereas if high predictive accuracy is the most important and you've got a massive data set, then machine learning would be sensible. I believe that experts in medical AI need to understand the strengths and weaknesses of both of these approaches, even if you don't specialize, even if you're not able to specialize in both, you really need to understand the strengths of both. So I'll stop there. Thanks for your attention.
Thank you, Jeremy. Before I open the questions, I want to acknowledge and thank you because I didn't introduce you at all. Jeremy Wyatt has been a physician in early stage of his career, and he did medicine in Oxford and in London, and he has enviable sets of publications. And even though he's retired recently, and his publication level, I think, has gone up in recent years. And he's been speakers in many conferences and
the book
speakers in many and his recent
the new edition is out.
new edition of the evaluation
Finally.
by I think with the Chuck Friedman and himself on the evaluation of the clinical information systems. So I've used it in teachings, and hopefully the others will do that. I want to thank him, and he's been a frequent speaker in our seminar series, and also he's been a speaker at Edge conference in Victoria. We are delighted always to have him as a speaker. Thank you, Jeremy.
It's a pleasure. Thank you. Thanks for asking me, Abdul. You probably won't ask me again now because I was late.
No. Always, as always. So I'm going to open the floor for questioning. Andrea, do you want to switch off the recording for your end?